Welcome, everybody, to RISE Learning Machines seminars. I am Olof Mogren, and this is a RISE Open Weekly Seminar on AI and Machine Learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working on AI to fight climate change. The meeting will be recorded, and if anyone wants to be removed from this recording, let us know. Also, there is a collection of great talks collected on our YouTube channel, so go check that out after this talk. Today, I will introduce Georges Le Bellier, who's a PhD student at CNAM in Paris. Georges is he's in his third year and will defend next spring, and he's working on efficient conditional generative models tailored to remote sensing. He's also working on flow-based methods and domain adaptation, and aiming to enhance the robustness of Earth observation models to shifting data distributions. The topic today is generative domain adaptation and foundation models for robust Earth observation. And with this said, I will stop my screen sharing and hand over the word to you, Georges.
Thank you. Yes. Can you see my screen?
Yes.
Yeah, okay, perfect. So thank you very much for the invitation. I'm very glad to be here to speak about two different subjects, but under the same umbrella. So generative domain adaptations and the foundation models benchmarking for robust Earth observation. And as you said, I'm Georges Le Bellier. I'm a PhD student at Conservatoire National des Arts et Métiers. I'm supervised by Nicolas Audebert. And I'm working in Paris, France. So as an introduction, I want to underline that we all know here that Earth observation data is very rich. We have very diverse source of data. We can have different areas also, and we can have time series. So we are dealing with very rich and various type of data. From a computer science perspective, it can be very interesting since we can capture more information about each type of data and the intrinsic characteristics they have. But it can be also a challenging topic from a deep learning perspective because we want to be able to extract some meaningful information from various data and to deal with various sensors, various areas, etc. So if we just imagine this little box represent the distribution of all Earth observation data, when we are trying to train some Earth observation models, well, we are restricting ourselves to a small part of this large distribution, and so we have a smaller training distribution. So the issue we have is that even if we are training in a self-supervised way or unsupervised, often when we are deploying our models in real-world applications, we have a distribution shift between our training distribution and our inference distribution. So here, for example, we have a small overlap between the two distributions. It can be, for example, some locations that are similar and we are considering the same type of sensors, but we can have some performance drop. But there are even more worrying scenarios where the training distribution is very far for the inference one. If we have different sensors, we can have this kind of shift, and it can happen in a lot of cases. For example, imagine that you train a model on optical data, and at inference time, you only have SAR data. For various reasons, imagine that the cloud coverage is very high these days, and so the optical data is correlated with clouds. So you use radar in order to see through clouds and have some insight about what is happening on the ground. But your model is not trained on SAR data, so you won't have good predictions. So the issue is the following, is that we have often distribution mismatch between the training distribution and the inference one. And in this talk, I will present two different approaches that are trying to build robust AI pipelines for Earth observation. So the idea is that we want to build pipelines that are robust against some different shifts, typically sensor, or natural disasters. The first approach is geospatial foundation model, and I depicted these kind of models with this dashed distribution because in this case, what we are trying to do is not to train a large model on the task we want and do inference on, but we want to learn embeddings that are providing meaningful information that will help us later to answer some questions about our downstream task. So the objective is changed, but we want to apply this model and train them on large distributions so we can have still meaningful embeddings to use later. And the second one is about generative domain adaptation, where we want to learn a mapping between the inference distribution and the training one. So we want to transport the images or any modalities that we have at inference to the distribution that were used during training. So I have two different parts in this talk. The first one will center around geospatial foundation models with Pangaea. That is a framework and a benchmark we propose in order to evaluate the performances of geospatial foundation models. And the second part will be about FlowEO, which is a generative flow matching model for unsupervised domain adaptation on Earth observation data. So the first one, Pangaea, is a project that was led by Valerio Mazzucci, and we want to do a robust estimation of the geospatial foundation models performances. So first, I will do a quick recall on geospatial foundation models. So geospatial foundation models are large models in most cases that are trying to learn useful for many tasks representation of Earth observation images and on large datasets. So the main idea is that we have a lot of sensors, we have a lot of data. Unsupervised learning allows us to learn meaningful representation of all those data and to compress the information in smaller embeddings. So you take your large amount of data, you want to learn a model that is able to compress each image, each data piece into a smaller embedding. And once your model learned how to produce those embeddings, you can learn small adapters in order to go from those embeddings to the task you want. So you can do wildfire detection, flood mapping, land cover. You just have to learn small adapters that I will use the embeddings produced by the geospatial foundation model and then do the downstream task. We have several objectives when we are building geospatial foundation model. We want the embeddings to be accurate for a lot of tasks. We want a model to embed some kind of spatial temporal awareness to be agnostic to the sensors. So if some sensors are not available at inference time, you want to be able to do some kind of predictions. And you want to take advantage of multimodality and the intrinsic characteristics of each sensors and the information contained in each sensor data. And you want to be able to use it in all scenarios. Nevertheless, there is a large list of geofoundation models, and if you have a real-world application, let's say you want to do segmentation of crops in the south of France, and you need to find a model to do so, you need to choose one of them, and you can't test all of them. It will be very costly. So we need a robust benchmark. Why? Because geospatial foundation model, in their original article, they evaluate themselves on very different setups. And so their training datasets are different, their inference datasets are different. So you can't just compare them in a fair way. So we wanted to build a benchmark that is targeting three different points. First, we want to assess the performances of each geospatial foundation model. We want to do it in a fair and robust way. which means that we want to include a lot of countries in our benchmark, not only Western country. Also, we want the benchmark to be usable and align with the need of big and large labs with small or large GPU resources. And we want our benchmark to give some useful insights for the next iteration of geospatial foundation models, so you can have some clue about what to do and what not to do. So we came up with this framework. So the Pangea team worked on that, this combination of different data sets and also different models. And we had several questions, research questions. First, how do the geospatial foundation models generate across domains, so across tasks, but also sensors? How do they compare to supervised baseline? So if you have a simple task to achieve, and you are asking yourself, should I use foundation models or should I use supervised baselines? In which context should I use UNet, for example, or should I use DOFA? And the last point is we want to see how the representation are relevant depending on the number of data you have. The hypothesis we had is that if we have very few data, then a supervised baseline will perform worse. So we compiled several datasets. I name a few of them here, just to see that we encapsulate a lot of sensors, and sometimes we also have multimodality. And all those datasets have one thing in common. They allow us to tackle pixel level prediction. We want to see if geospatial foundation models are able to do good predictions, but go above patch level prediction. So we are not interested here in classifications, but mostly on segmentation, regression, for example, biomass regression, and change detection. And as you can see, the data sets covers a lot of different areas in the world. We had to choose some geospatial foundation models in order to have a fair comparison between them. And so we started with several criterions. The first one is we required our models to be open sourced, so people can have benchmarks they can reproduce themselves. And also we want to be able to load the model and train them in different scenarios. So that was the first point. The models needed to be open sourced, and we evaluate also the impact on the community. One thing I want to underline is that this work started a year ago. So in the preprint, there is only models that were already released at that time. Okay. So now that we have our dataset and our models, we need an evaluation protocol, and we needed to start from the data. So we need to do some dataset preprocessing because, as I said, geospatial foundation models were trained on different datasets. And we needed to set an unified way to preprocess all our data. So what we do is simple boundwise normalization. For each dataset, we compute the mean and the standard deviation, and we scale our data with respect to that. So all models have the same inputs. And also we had to do a bit of band matching. So if your model is taking as input RGB, and we only have Sentinel-2 data, for example, then we will select the three bands that correspond to RGB to inside the Sentinel-2 data, and we'll feed the model with them. And the other way around is your model is trained on Sentinel-2 data and we only have RGB. We are doing zero padding for the missing bands that allows us to use, let's say, the models in their full capacity for all datasets. And we have a simple protocol for training our models. So as I said before, we want big and small labs to use this benchmark. And for most of the lab, it is not possible to fine-tune an encoder, a geo foundation model. So what we are doing is that we are really in the setup where we are considering foundation models as encoders, and then they are frozen. Their weights remain the same during the training, and we are only training decoder, UPNet decoder. So I have my initial image that will go through the encoder. I will select 4 different stages to extract the embeddings, and then those embeddings will go through the UPNet decoder that will transform those embeddings into dense prediction. So the model prediction is dense. It is compared to dense labels. And then we have a loss function that will help us to tune only the decoder. We also have some multi-temporal datasets. The issue is that we have geospatial foundation models that are not aware of time embedding and they don't take time series as inputs. But some of them do. For example, predv. So for predv, we feed the model with directly the time series, and it will give us some predictions. But for the other one, we'll just feed the model with a single frame of the time series and ask the encoder to produce the corresponding embeddings. We'll concatenate the embeddings obtained and then go through an aggregation layer. So it can be a linear layer or LTE, so it's a lightweight attention module. We merge the different embeddings obtained for one time series this way, and then go through the UPNet decoder. So this way we can use single temporal models on multi-temporal datasets. And we evaluate 2 separate things. We also check if our models are great in data scarce setups. So we only consider that we have 50 or 10% of the training dataset to tune the decoder. The hypothesis here is if we have very few data, then the representation learned by the geospatial foundation model will be more and more useful. And one safety check that is very important to do, I think, when we are dealing with this benchmarking geospatial foundation model, is that we want to see if we are training from scratch some supervised baseline, so UNet or VITB. In this case, are we able to overcome the difficulties we can have with supervised approaches? Okay, so we had some results. And the first one is when we use all the data available for each dataset, and we are depicting the performances in terms of segmentation or regression here. I will not go into details. I just want to focus on the last column, the top 2 ranking. So the top 2 ranking is about the number of datasets where the model was in the top 2 best performing models. So if we look at this column, what we see is that UNet baseline, when you have access to the full dataset, achieves very strong results and actually beats the other geo foundation models. But if we look at other scenarios where we have only access to 50% of the data, of the labels, what we see is that first, previously we were 6 times in the top 2 ranking, but this time UNet is only 4 times, so it's performing worse, and we can see the emergence of some geo foundation models in the top ranking. And actually this trend continues. If we only have 10% of the labels, then Chroma is clearly above UNet, and we have other geospatial foundation models that are also beating UNet. So the main message here is that if you have a large enough dataset that is not that large, I mean, some of the datasets here are academic datasets and not sufficiently large to train large models. But if you have very few datasets, very few data points, you may want to use the useful representation from geospatial foundation model. Otherwise, if your model is sufficiently large, you want to use a unit baseline and do it in a supervised way. Okay. One very interesting insight we had is about the pretraining resolution. So one thing we noticed is that if you're looking here, so at GAOFN2 data, the best performing models on the GAOFN2 data are the ones that are trained also on high resolution datasets. So if your model is trained on high resolution datasets, you will have better performances on high resolution datasets. And in the same way, we saw that if we look at the best performing dataset on Sentinel-1, Sentinel-2 data, it will be Chroma. And Chroma was trained on Sentinel-1 and 2 datasets. So it looks like the promise that was done before that geospatial foundation model might be sensor agnostic is not completely true. And in some cases, you should look at the bands that were used during training in order to select your best performing geospatial foundation model. So before looking at the size of the model or the size of the training dataset, maybe start with looking at the bands that were used during pre-training. Okay. So I will conclude on Pangaea. Pangaea is an open source code base, so feel free to participate in it. It also includes, so all the datasets that are included in the preprint paper are included in the code base. So it can be also a way to integrate a new dataset to your pipeline. We had all the geospatial foundation models that are included in the code, all the training processing, the evaluation protocol. There are already some papers that are using Pangaea in order to do their evaluation experiments. So an ESAT that was accepted at CVPR this year, TerraMind by IBM, also accepted at ICCV. So next steps are to improve the code base in order to include more datasets and models. And feel free to add your contribution to this project.
George,
Yes.
there are a couple of questions if you'd like to take them now.
Yes. Maybe, yeah, I will answer the first question before going to the second part.
So there's a question in the chat. For someone running this benchmark, do the user need to tune the hyperparameters like learning rate, weight decay, segmentation thresholds per model and per task? How would you suggest this tuning? Should this be run across multiple random seeds?
Okay. So those are questions that we had. And in our protocol, we selected values for each parameter. So as you said, learning rate, weight decay, etc. Knowing that for each dataset, we are only tuning the UPerNet decoder. So it is not like if the weights we are trying to tune are very different from one setup to the other, despite that there is still the embeddings that are changing. But so we have a set of hyperparameters that you can use in order to compare to other datasets that are in the paper.
Okay.
And yeah.
I also have a question about the evaluation. So you're taking two scores. You're taking the scores of the reconstruction of the original image from the UPerNet. Is that right?
We don't use any reconstruction score here.
But you have a dense prediction.
Yes, but it is tuned with labels you have.
Okay.
Yeah.
Okay, I see.
Yeah, the UPerNet is just an adapter, let's say, to the
I see.
task you are trying to have.
Okay.
And I also have a question at this stage, if possible.
Yeah.
So I was wondering, when you compare like geospatial foundation models to the supervised baselines, and you then look at different label regimes where you saw that the supervised gets worse, as expected, I guess, when you have fewer labels. I suppose that the supervised models were like somehow trained from scratch, or was there also some pre-training stage which would alleviate for some of the loss in labels, so to say?
No, the supervised baselines are trained from scratch with only 10% of the data, for example. So as you say, the main difficulty for them is that they have to learn some kind of representation of the images, and maybe they don't have enough data in order to do so, and then to learn how to solve the task.
Yeah, so that makes sense. But I was thinking that, yeah, I mean, maybe we can discuss more later. I was more thinking that maybe it would be interesting to see, because it's also quite common in these settings to do the pre-training in some sense. Like if you have few labels, a typical approach would be to do some sort of pre-training and then do supervised fine-tuning, in which case the supervised model might actually be better in relation to the geospatial foundation models than your results would suggest, so to say.
Yeah, okay, I see the point. So you suggest that we have a unsupervised pre-training with like 10% of the data. Okay. Yeah, it can be very interesting to see, even if with few data we can mimic or at least learn some useful representation. Yeah,
Yeah, thanks a lot.
thanks. Okay, so maybe if we don't have any question, I can move to the second part of this presentation. So the second part is about generative domain adaptation, and it's a project I'm currently leading. So this one is an article that will be available on archive soon and published hopefully later. And the setup is common to the introduction I made before. So in Earth observation, we have heterogeneous data, and we are facing a lot of distribution shifts. So there are quite few of them we are interested in this case. First is the changes in sensors. Second one is you have two different images of the same area, but one was taken before the flood and the second one after the flood. And the last one is you have two different areas on Earth. So imagine that you train a model to do segmentation in South Africa, and you try to apply it in the USA, it will not work. So what we are trying to do is to bridge these distribution shifts so we can use pre-trained models at inference. So here I have trained a segmentation model on my distribution that is depicted in green on optical data. And if I'm trying to apply the same segmentation model to SAR imagery, it will not work and have a domain shift that is quite important. So the setup we have here is that we have pre-trained predictive models, and we consider that they are frozen. We have them off the shelf, and we don't want to touch them. And we want to build domain adaptation methods that are independent of the pre-trained model, and we will not make any assumption on the architecture or the features that they can provide. Also, second constraint, we want to do it in an unsupervised way, so we'll not use any label. So domain adaptation, and more specifically, generative domain adaptation, the way we consider it is, as I said before, if my model was trained on optical data and I am playing it on SAR data, then the domain shift hinders the performance of the model. So what we want to do, in the pixel space, we want to apply generative models and to do the generative domain adaptation. And so we'll transfer the initial image to the training distribution, so we can then use pre-trained segmentation models and apply inference. So the point is really, we have a domain shift, we have a gap between the orthogonal distribution. We want to bridge it with a generative model. The main advantage of this unsupervised domain adaptation compared to other ones, for example, the domain adaptation methods that are using embeddings, is that we have visual controls. So imagine that you generate a lot of images with your generative domain adaptation. You can look at the quality and the artifacts that there are in the transferred images before feeding your segmentation model with them. And if you are doing domain adaptation in an embedding space, you have very few controls and way to look at how the adaptation performed. So it improves explainability, and also it is easier to tackle dense tasks if you are directly in the pixel space. Lastly, what I want to underline is that our generative domain adaptation is independent of the downstream task. So we are still in the pixel space and make no assumption on the downstream task. So the main goal is to use generative models to bridge the two distribution while preserving semantic information, because it is the information we want to transfer for the different tasks we want to assess. So those ideas are not new. There is already some approaches that are using such setups, such as pix-to-pix or cyclogram, were used for domain adaptation. But we have seen the rise of diffusion models and more recently of flow matching models that are really powerful generative models. And we want to see, can we adapt them to our task? So I will do just a quick introduction to flow matching because it can be useful for later. And flow matching models are a generalization of diffusion models where you bridge two different arbitrary distribution. So in current papers, published papers, a lot of them are using flow matching models the same way that we used diffusion models. So in a generative setup that go map Gaussian distribution to data distribution. But the interesting part about flow matching models is that you can do data-to-data translation. And to map the P0 to P1, we have to learn a flow that is depicted by this equation. And we just have to learn a velocity field u of t that drives the point from the initial distribution to the target distribution. So if we have an image from the initial distribution P0, so it's x0, this image, that was taken after the flood, for example, and we want to map it to the images taken before the flood, we'll start from x0, and once we've learned how to estimate ut, we can solve the flow equation using like ODE solvers and just follow the flow. It will give us a series of xt, and at the end we'll arrive in P1. And P1 will be, x1 will be an image from P1 that is depicting the same location, but before the flood. So to train flow matching models, I won't go into details. I want to just highlight 2 points. First, we have to select pairs of data. And this is an important part that I will center around later. But you need to select x0 and x1 into a joint distribution. It's called a coupling, but it's just a way to say that we need to find a way to select pairs of images. And then the process is very simple. You just have to sample time between 0 and 1 and create an interpolation between x0 and x1 that will give you xt. And you can estimate u of t by just solving this regression objective. So as we saw the slide before, we want to learn u of t, ut, and we can do so with a simple neural network and a simple objective that is just we want to estimate x1 minus x0. So the first question is, if I want to apply this flow matching setup to my data-to-data translation, I have really the choice of the coupling to figure out. So I want to create pairs of data that are meaningful with respect to the transport I want to learn. So the transport I want to learn must preserve semantic information. So the idea is that if I want to learn such a transport, I should have such couplings that are preserving semantic information. So we were thinking about classifying our datasets with respect to semantic alignment. The first one is I have two different locations on Earth, and I have no information about the labels because we are in an unsupervised domain adaptation setup. And I want to create pairs from both distributions. A priori, we don't have any knowledge on how to create meaningful pairs with respect to the semantic, so we are choosing independent coupling. But so this is a really complicated, complex case, but we have easier ones. So the first one is weakly aligned datasets. If we are considering here, for example, SpaceNet 8 dataset, we have pairs of images, same area, that are taken before and after the flood. So we have a lot of semantic changes because of the natural disaster, but also because, for example, clouds coverage is different in both images of the pair. So we don't have exactly the same semantic, but we suggest that in this case, we may choose data-dependent coupling, which is just a probabilistic way to say that if I select in my initial distribution the image taken before the flood, I have to choose the corresponding image taken after the flood. So this is weakly aligned in the sense that the semantic alignment is pretty weak, but we have co-registered images. And the strongly aligned scenario is that we have pairs that are really depicting exactly the same objects, but for example, with different sensors. So if you think about super resolution, sensor translation, in most cases, you will be in this case. And in this case, we use natural pairs, let's say, as data-dependent coupling. So the full pipeline of the dataset will center around the two different weakly aligned and strongly aligned scenarios. And we are leaving the unaligned scenario for further researches because it's really other consideration to take into account to make it work. So I will now introduce FlowEO. FlowEO is our flow matching model for Earth observation unsupervised domain adaptation. And we have a simple training process. First, we'll choose the pairs with respect to the coupling. As I mentioned before, we will encode each image into a latent representation. Here we are using a latent space that is dedicated for generative applications. So it's the same one as Stable Diffusion 3. So it's really a way to compress information, but still retaining a lot of information so you can generate new images. And then I will have the usual flow matching training steps. So the interpollant, and then the velocity prediction that we are doing with a unit backbone. So as we mentioned before, we are regressing the conditional velocity. So this term is Z1 minus Z0 with a neural network. And as you can see, I don't use my predictive models in this pipeline, and there are no labels used during training. Okay, and at inference time, what we saw is that at inference, we need to solve the flow equation, which is this ODE, and with the velocity field UT, that is approximated by the learned unit. So we'll just take our first image, encode it into the latent space, use ODE solvers with the velocity approximated by our frozen unit backbone, and then decode the image. So it's just numerical integration of this equation and encoding decoding. And once you have done this adaptation step, you can plug any downstream task model you want to apply on this generated image. It can be classification, it can be segmentation, it can be regression, it can be a lot of stuff. So we made several experiments on different datasets. So we have, as I said before, strongly aligned datasets. So here we are mainly tackling cross-sensor translation with SpaceNet 6, Sentinel-1 Flood 11, and BiggerSnap 2. And also we have weakly aligned datasets in the case of natural disaster as flooding on SpaceNet 8. And we considered also subset of SpaceNet 8, such as the Germany and Louisiana subset. We had some baselines that were trained with the same pairs that we use for our model. And those baselines are both unsupervised domain adaptation, generative domain adaptation baselines, such as Pix2Pix and CycleGAN, but also some data-to-data translation models, such as StegoGAN and UNSB. For FlowEO, as I said, we use a Stable Diffusion 3 latent space. So we reduce our initial images that are 256 to this dimension, so lower dimensions, but we have 4 channels, and we are using a simple unit backbone. And one of the main contribution of the article and this research project is most of the paper, when we are dealing with generative domain adaptation, often we are looking at generative quality. And we are looking, for example, at some fit score or LPIPs. But what we did, we also evaluated on the downstream task or domain adaptation method. So we compare the performances of segmentation models on the generated data. So some images and results we had on strongly aligned datasets. So the first column is the initial data. So we are starting from these SAR images, and we have these component, these optical images in the dataset. Here are the prediction by the segmentation model, the ground truth annotations, and then for each model we are depicting the images generated, the prediction of the segmentation model on the generated images. And what we can see is that the generation quality is high for the FlowEO model and really on par with different other models, and even better than few of them. But the most important part is that the prediction provided by the segmentation model on the generated images by FlowEO are closer to the ground truth than other models. And if we look at the metrics, so as I said, we are looking at generative metrics such as feed and LPIP. So we had good generation quality, let's say, but we had also great performances in terms of segmentation scores obtained by the segmentation model on generated data. What you can see is that on strongly aligned dataset, Pix2Pix is quite competitive since it was designed in the first place for aligned data translation, but FlowEO has better results in most cases. And more interestingly, on weakly aligned dataset, we have similar conclusions. So this is the image taken after the flood, and we want to map it to the distribution of images taken before the flood. And segmentation models performances are better. But what I want to highlight also, and what struck me at first, is the fact that the flow matching model is the only one that is able to correctly translate the state of the river. And we see that after the flood, there is a lot of wavelets, and in some cases, there are some elements also in the river. And the flow matching model is able to map it correctly to a calm river. And yeah. So we had good performances on weakly aligned dataset, and it is confirmed by the different metrics we evaluated. So I will conclude on this part. The flow matching models we propose, FlowEO improves the segmentation score in different generative domain adaptation setups, and it works well for weakly aligned, strongly aligned dataset. Few experiments we made on unaligned dataset show us that it is not working that well. The main difficulty is that we need to find ways to build meaningful pairs, and those are the next steps we want to do on this project. Is how can we build meaningful pairs in order to train our flow matching models to do translation between two different distribution for unaligned dataset. One thing we noticed also is we fine-tuned the VA decoder, and it improves the results, but from the generative line of work, let's say, on Earth observation, I think it would be very beneficial to the community to have a VA that is designed for generation application, so similar to Stable Diffusion VA, but for remote sensing data. And so we can train a lot of generative models, but also domain adaptation generative models. And it looks like it is a bottleneck in the current setup in order to apply this type of approaches to new scenarios, new kind of data that are really different from optical one. And we wanted to test it on new setups. Imagine that you have a multimodal dataset, SAR and optical data. Maybe you can do data augmentation by generating new pairs of SAR and optical by generating this optical part from the SAR data, etc., etc.